Titrations. Hey, we've used that word before, titrations, in Unit 2. However, while we were doing it back then, it was just, we were just finding molarity through titrations. And it was very simple. Like, some of y'all thought that was difficult, but now you've been in the class for a while. And you wish we could go back to Unit 2. But these are the real titrations. Now, we're going to be doing this in lab when you get back from break. All right? Here's what a titration is. There's going to be a sample, and it could be an acid or a base. I'm going to say a base. All right? There's going to be a sample of a base in a titration. All right? And what we're going to do is add a sample of an acid to it, a drop at a time. All right? And what you can do is you can watch the pH slowly change. All right? In this case, the pH would be going down because we're adding the acid to the base. Now, this would be a burette, and it would be graduated, meaning that right here it might say 50 mils. All right? Which means if the water went down to this mark, down here at the 40, 30, 20, 10 mil mark, all right, you would be able to see, okay, well, I've added 40 mils of acid. What has that done to the base? And there's a bunch of different calculations you can run to find concentrations and pH and pOH and stuff like that. This is the experimental setup of your titration. It's important for you to visualize this as we're doing these problems. Now, the most common use of a titration is when you don't know the molarity of this. All right? If this molarity is unknown, it turns out that if you do know the molarity of this, which of course you would, you set up the burette, that based on the identity of the acid and base, and based on the amount of acid you put into the base, by the time that you're able to reach what's called the endpoint, when you make it hit a pH of roughly 7-ish, there's a calculation you can do to find this molarity. We're not going to do all that today. We're not doing the unknown. We'll do that in lab. What I want to show you today is just the basic math associated with this titration technique and changes in pH. There is a little bit of vocab that's important. The equivalence point is going to be whenever the amount of moles of this is equal to the amount of moles of that. The moles of acid equal to moles of base. You'll see it happen in a problem today. Maybe only one because I'm going to be recording through lunch again. But it's when the moles of acid equal moles of base in the beaker. So keep in mind, this is where everything ends up, right? We start with a set amount of base and we'll never change it again. All right, however much base is in there is how much will always be in there. The only thing that we're altering is how much acid is being added. So this amount of liquid is going to keep going up, right, as we're adding more volume of other liquid to it. So keep that in mind. So there's things that will always stay the same, the amount of base, all right, the amount of initial base, and things that are going to change, the amount of acid being added, the amount of volume in the beaker, and whatnot. So let's not have fun. This first problem says that you're adding KOH to HCl. It says we're adding KOH to HCl. Yes. So what I noticed right away about this titration, all right, well, first off, this is what's in the beaker, the HCl, and the KOH is what's in the burette being added to it, yeah? But I noticed that it's strong. Do you see how it's strong? Strong strongs are different than strong weaks. And you're going to see that as you finish the video later. Because I only have time to get through a problem and a half today. But they're quite different from each other. So we're doing a strong first. All right? Now, we're just going to go through the steps and see what it tells us to do. Step 1. Calculate the pH before the invasion. All right? It wants to know the pH of this solution before you add any of him. All right? Now, it's good news that it's asking for the pH of a strong sample, right? That's our favorite thing to do in here, or it should be, is finding the pH of a strong sample. Because how do you do that? Negative log of the molarity. Do we have a molarity of the HCl?
Yes.
We do. It says that the HCl has a molarity of 0.8. It says that the HCl has a molarity of 0.8. All right? And if I'm looking to find the pH of a strong sample, it's just the negative log of that concentration. I get 0.097 for the pH. Yep, 1, 2, 3. In a pH calculation, all digits to the right of the decimal are significant. All right, hey, we've already done the first one. That was easy, right? Yeah. Class dismissed. Happy Thanksgiving. Now the invasion begins. All right, now this is going to flash back to what we've been doing in this unit in regards to the steps of an invasion. Find the moles, find the limiting reactants, subtract. All right, so hopefully we're getting into a rhythm. So let's see what's going to happen. Step 2, calculate the pH after you add 20 mils of base. Now, it's strong. If you remember the way our invaders looked when there was a strong species, I only cared about H plus or HO minus depending on base or acid, all right? Since they're both strong, that's still all I care about. So what are we mixing together? We are mixing together, what's being added to what? I forget, base to acid. So I am adding a strong base to a strong acid, all right? And he's right, it always forms water, right? So this is what the invasion will look like the entire time. Because remember, I don't want you to think these are random words. Imagine the experimental setup. I've got the beaker of acid, and I've got the burette of base just being added into it, all right? So this is what's going to happen as the invasion continues. Now, like I said, the beaker is never going to change how much initial stuff we started with. Once we have our acid here, we're just adding base to it. We're never adding more acid to it. We're just adding base to it. So my point is, however many moles we're about to calculate that we start with H plus will be the amount of moles that we started with for the entire process. We only have to calculate it once since we're not going to be adding any more of it. Now, how do we find moles? Well, we've been doing lots of that. All right, remember, to find moles, molarity times volume, right? So look here, we've got that. HCl has a molarity of 0.8 and a volume of 40 mils. We have a molarity of 0.8. All right, and we've got a 40 mils. So that right there will give us moles. Are you okay? Moles of H, yeah, because I pulled those numbers from the acid. So I'm going to get a mole count of 0.032. All right, and this value will never change throughout the rest of the slide. It'll never change because this is what's in the starting beaker, and we'll never alter that. That's 3 sig figs. Leading zeros don't count for moles. All I can do is keep saying it. Eventually, your brain has to accept it.
Isn't it 4 to the right?
No, leading zeros are never significant.
It's not pH.
And it's not pH. Okay. All right. So what about the OH? Well, I have a molarity of the OH. Do you see the 0.6? We haven't used it yet, but we've got 0.6 molar of the base, but the amount of him keeps changing. All right. Hey, how much of him are we going to add initially? 20 mils. 20 mils. So I'm going to multiply that by 0.02. Yeah, still number 2. Yeah, we haven't. I have to circle a pH first, not to be on number 2. We're trying to find a pH. I haven't done that yet. All right. Trying to show all my work here. So this is going to give me a number over here, and I'm going to get 0.012. And there's my mole counts. This should feel just like the problems we've been doing. What do?
You subtract the small
Subtract the smaller number, it's limiting reactant. So let's go minus 0.0120. Minus 0.0120. Water's hanging out over there, but we know that he is inconsequential for any of this, so we're just going to ignore him. And we get 0.02 here.
This is in the rice table now, right?
This is what actually referred to as a stoichiometry table. I just don't call it that because it's not like a published word.
Okay.
But this is not a rice table.
Stoichiometry was like dimensional analysis.
Right, but this technically is, we're doing stoichiometry because we're doing a multiple comparison to find limiting reactant right now. It's just, you're better at it now than you think you are. Hey, check it out. This is the mole count that's left. We can now use this to find the pH, but we know to find pH, we need molarity. So what would I want to divide these moles by in order to turn it into a molarity?
60 milliliters.
Hey, what was the answer?
60 milliliters.
Why 60?
Because 20 plus 4, that's a new volume.
My beaker had 40. We dropped in 20 of the base. Now we're at 60 mils. So we are going to divide him by 0.06. And that'll give us, yes ma'am.
When you're finding out the mole count for the base, where'd you get 0.02 from? Like they're here.
20 milliliters. That's 20 milliliters written as liters. All right. Now, my answer that I get here is 0.333. And that's molar. And to find pH, that's real easy, right? Look, it's strong. So to find pH, it is the negative log of that concentration.
I thought molarity was supposed to be moles divided by liters.
Yeah, moles over by liters equals molarity.
Did you say like the AP chemistry people?
Oh, moles over liter. Yeah, and that's amazing that you remember that. It was in my first lecture that I brought that up. Yeah, but as I've been continuing to research through, they're still interchangeable. So, no, they definitely can't take off points if you use the capital M. Yeah, I keep learning with y'all as we go. Hey, do y'all get 0.477? All right, which is a super acidic pH, right? Like that's a strong acid. And hey, look, hey, it all makes sense. What's that? No, I'll get some out for us to drink during lunch. I don't know. What was that other number?
Oh, yeah.
Should it be an 8?
It should be 8.
Should it be 8? Okay.
What did you point at and say it makes sense? Did you point at the black one?
I pointed for the fact that the strong acid wins, which is connected to a pH that's really low.
Okay.
Right?
Oh, yeah.
A pH below 7 is acidic. A pH far from 7 is strong.
Okay. I thought you were saying there was something apparent in the equation that was telling us.
All right, so we solved the titration. Now look what happens, guys. They just keep adding more.
Yeah.
All they keep doing is adding more, which means this gets quite repetitive. Now watch, I know you don't have a whiteboard, so you can't do this, but I'm going to selectively erase just to show your brain the amount of things that stay constant, all right? This amount's gonna change. This stuff's gonna change, all right? Now, I could erase him. I mean, I could leave him up there because he is always giving us this number. I want the board space though, all right? But anyway, but look, this is not gonna change. The amount of acid that started in the beaker, always the same. And the invasion is always the same. But now, we're gonna take a look at the next one. It says, find the pH after 40 mils of base. Well, hey, the molarity of the base didn't change, right? Because that burette that we're adding the stuff to, it's 6 molar. The whole time it's 6 molar. The only thing that's different is how much we've added. Yes?
Why does the amount of the base change?
Because in this step right here, we've added 20 mils. In the next step, we've added 40 mils, which by definition is 20 mils more, a new amount.
Okay, I get it.
All right? So, but now it's 40. So to find moles, I'm going to multiply it by 0.04.
Wait, is this step 3 or what?
Yeah, I'm on bullet 3.
Wait. When it says like it goes from 40 to 40, is that like 40 more?
No, not more. It's we had our burette and the level, that graduated level, had gone down 20. It wants to know, well, what happens when the graduated level had gone down a total of 40. It will never ask it in the other way that you were just thinking. It'll never say 40 more just to be mean. All right? I get a value here of 0.024.
Yes.
The smaller number loses.
Will the constant always be the bigger
I
number?
want to whiteboard. I don't like.
What did you just ask?
I said, will the constant always be the bigger number?
No, they'll switch. Eventually the other guy will win.
You know what I'm saying?
No, what do you mean the constant?
Like
What-
the H, since it has the same number the whole time, it's been the biggest one.
Yeah, so no, it won't always be
It won't
bigger.
always
No. And then we're sitting with 0.008 here. All right, there's a mole count. Are you with me?
Yes.
All right. Now we want the pH, so we need molarity. We know the moles.
So we have to add the liters.
Well, divide by the liters. Yeah, but you're right. But they need to be added together. So hey, look at my beaker. Do you see my beaker? Do you see the beaker? How many mils are in there now?
80 milliliters.
There's 80 milliliters, 40 and 40.
You show these videos to your children.
No, there was one day a couple of weeks ago that I came home and my wife over dinner asked me a question. She was like, "So what happened with this? And I was like, "What did you just say?" Like it was really wicked. But she said that she had watched some of my video from that day and she thought it was funny.
When you said, "I will kill you."
I will kill you. Well, she's used to hearing that. Okay. So I get a molarity here. I'm sorry. Yeah, a molarity of about 0.1.
Wait, when we put like a 0, 0 or anything.
Well, there's only one sig fig, so technically. Sorry?
Oh my god.
All right, so now we go negative log of that concentration. Now, guys, remember, the only reason this whole negative log nonsense is working for us is because we're analyzing a strong the whole way through. All right? And I'm going to get a pH of about 1.
It's nice. It's really
I lost track of all the numbers.
Ask a more specific question.
Okay. Okay, so
Here, just let me do it then. This number is constant. All right? This is the molarity of the intruder times the amount that we added, which gave me that number. I compared them. This was smaller, so I subtracted the smaller from both. He lost. That's what was left. So this is the moles that we have now. If you divide moles by the liters that you have now, it gives you molarity. The negative log of a strong sample gives you pH. We okay? Let's go again. Hey, look, we're adding a different amount. Rinse and repeat, right?
Wait, are we on bullet 4?
Yep, this will be bullet 4 with the number 53 in it. I'm going to selectively erase so that I don't have to rewrite as much stuff as y'all do. Hey, look, you know what I erased last time that I shouldn't have? The 0.6. Remember, that 0.6 is the molarity of the base that's being added, and it won't change either. So I'm just trying to get as much of that in your brain as I can. Hey, how much is my intruder this time? 53 mils. So we want to multiply it by 0.053.
Yeah.
To get my new mole count. Point something.
Will there be
0318.
318.
Will there be this on the test, like bullet points where it's like do this, find whatever?
There's one question that looks just like this.
Yes, you do this.
And it's heavily weighted, y'all. I can change the point values of the individual questions.
It's only 7 questions.
And one of the questions looks exactly like this.
Only one?
I had to be careful. I'm trying. I have to feel it out. Y'all are the first group that I've done this with. So
It needs to be a 53.
yeah, they're gonna take a different test.
subtract the smaller number.
You got it.
2 tests ago, everybody was stressed out about the time. Last test, almost everybody finished early. So I'm feeling it all out as we go.
Isn't it gonna have like a 7 question?
Right now, well, in its current state, but I'm still Nothing's final. I have a whole Thanksgiving break to be creative.
Oh, yeah.
All right, now I get 0.0002. Do you?
Yes.
And now y'all should just be getting bored with this because it's just the same thing over and over again. Here's the amount of moles, but I want the pH, so divide moles by liters. Hey, what's our total liters now?
0.930.
93 milliliters.
Sorry, I meant 6.0.
Drink your Fanta.
I'm going to get a concentration of 0.00. It's only, I mean, I guess it's 0.002. I hate 1 sig fig more than anything.
Wait a minute, what? I got a different number than
That isn't the first.
I definitely got
Wait,
2.15 times 10 to the negative third power. What?
I got
You got that?
1.8.
I got what he
I got what he got.
Okay, maybe I did wrong math.
No, I got Mr.
Oh,
Oh, yeah, okay.
Wait, what'd you
Yeah, I'm good. So then we go negative log of that concentration is going to give me a pH of about 2.7. And if you look at our pHs, you'll notice that it's doing exactly what you expect it to do because every intrusion is an addition of base. So every intrusion should be raising the pH. Now, the questions are about to switch up a little bit, so you want to refocus your brain. Because we could ask, I mean, I could change these numbers forever and just have you do this over and over again, right? So let's take a look at what else it might ask you for. Bullet 5. Calculate the volume of base needed to reach the equivalence point. Can somebody remind me what equivalence point is? Moles of acid equal moles of base. Now, our moles of acid can't change. Therefore, what must the moles of base be for the equivalence point to happen? So, what I'm going to do is I'm going to just set the other value equal to the moles that we know have no variable in them. And now we're at the equivalence point. Now, it wants to know more. It doesn't want you just to draw a happy numbers matching. It wants you to analyze it, but that would be the equivalence point. So, just for fun, let's go ahead and show what happens, of course.
But wouldn't it want it in liters? What is this step doing?
So,
It does. It wants it in. I mean, the question wants volume, but I haven't showed you how to find that yet.
Oh,
All I've showed you is that we have none of each, right? In this case. Now, but if you look at the question, it turns out you didn't even have to do most of this to find the volume that needs to be added. Because here's what I know about the connection between all the values. I know that molarity equals moles over liters. This question is simply asking for the L, right?
Oh, so you just plug
So
numbers.
we already know the molarity of OH is that dude right there. It's 0.6. All right? We already know the moles of that dude at the equivalence point, 0.0320. What we don't know is how much of him we had to add into there to make those moles equal each other. But I bet you could solve for X here. Golly gee.
Yeah.
So hey, both of the answers are technically correct, but you'll see based on the follow-up questions that milliliters is always more handy to use. I mean, they're both in there, but they're going to stay bonded together unless you do a chemical reaction. All right, so are we okay with that? We found the answer. We have one question left, and we get to move on to a new titration. Woo! Finally. It says, oh, wait, hold on. It doesn't ask this, but it could. What is the pH right now?
7.
Why must it be 7?
Water's always 7.
Because even though we've been ignoring water, it's been continually producing water. This has been happening the whole time. But this is the only circumstance where everything else is suddenly gone. So now, suddenly, as Dylan's super excited about, this reaction is drinkable. All right? Right now it is. If you mix it in exactly this way, you have a glass of water.
But one slight mistake and you're dead.
One slight mistake and you are dead.
Can you try it?
So I want to have an equal amount of hydrochloric acid and potassium hydroxide.
Now, the last problem, though, is going to require you to really be self-aware on what you've done. By the way, guys, this idea, listen, a strong titration will always have a pH of 7 at the equivalence point. A strong titration will always have a pH of 7 at the equivalence point. I make that point because that is untrue for a strong-weak interaction. All right?
How do we know what the pH is again?
The reason we know automatically the pH here is 7 without doing anything is the only thing left in my reaction is water, and I've memorized water's pH.
What's water's pH? 7?
At 50 or 40, it goes from 1 to 2.7, and then you add 3 more, and it jumps to 7.
Crazy, right?
How do they do that?
Oh, I don't want to erase that. Oh, yeah, no, I do. You're going to get to watch it happen on Monday. Well, a Monday from now.
What is my pH at 9.7?
All right, here we go.
I die, right?
So, looking at the last one, all right? It says calculate the pH after adding 5 mils of NaOH past the equivalence point. Now, we need to be really aware of what it wants us to do here. Hey, this value right here is the amount we have to add for the equivalence point. Do you agree? All right, that's the amount that we need to add. All right, hey, how much volume started in? What was our initial volume? 40 mils. All right, so that's another important number. All right. And then this problem wants us to add how much extra?
5.
It wants us to add 5 more mils. Now, there's a lot of numbers here. All right, we'll call this our extra.
You wrote this as 9.
All right, what?
Your numbers?
Your Roman numeral's wrong.
I stole this because I cut out questions. It had you do more titrations. All right. Look, shh. All right, y'all are making it so my lunch is shorter. All right. I love answering your questions, but make them worthwhile. Now, all of these numbers are going to come into play here. It says calculate the pH after adding 5 mils past. So if I'm going to add 5 mils past that of 0.6, right? It's the base that we're adding, which has a molarity of 0.6. How much have I added if we're 5 mils past the equivalence point? 58.3. Because we've already added the equivalence point. It wants us to go...
Whoa.
We've already added the equivalence point, and it wants us to go 5 mils past. So it's 58.3.
Or NaOH, KOH, the same thing.
Oh, okay.
we're just one thing.
They were. It's another typo, but yeah, they work.
Wait, what is that? What is that?
Nothing yet. All I did was state facts. We started with 40. The equivalence point was 53, and the extra's 5. All right. I just want us to be aware that all of these values exist. Now, this times this, as we've done a bunch of times so far, is going to equal 0.035.
How many questions are in the homework?
Probably too many.
What is that?
All right. And now, same thing. Nothing's changing. All right. I figured out the value. I'm going to subtract the smaller number, which, watch Annalise, now it's this dude.
I'm watching.
I know, but that was your question earlier.
Oh, I was like,
The war has been lost.
Annalise, get off your phone, please. I know. Shit.
I was gonna say, whoa.
Just messing with you. Life is good. All right. And it looks like I'm going to get 0.0030. Now here's, some of y'all are confused why we wrote all these green numbers. It's for this. It's for you to see this part. Here's my mole count, right? It wants to know the pH. Now notice that we're hydroxide now. Yeah, it's going to give us pOH. But I need to divide the moles by the liters, right? How much total is in the beaker?
A lot.
98.3. All the information was there for you to see, but y'all are very bad at finding that number. You get so bogged down in everything else that you've done that you miss how to find that amount. And it's because the beaker has all of these in it.
So you just add all of them together?
With them written on the board in front of your face, yeah, it's so easy.
Then why didn't we just do it like that? Why'd you take it through all the math?
All right, now I'm able to use that to find my molarity. All right, I'm going to get a molarity of 0.03.
Oh, we used the math to find that.
What do y'all get? 0.0303?
I got 0.0003.
Oh.
Gabby, are you leaving?
Excuse the interruption.
Yes,
Could you please send Giovanni Bettis to attendance at his point home?
on his way.
Thank you.
What's this other digit? 5?
Yo, literally got 1,000
I got
right there. I was like, oh my God, my heart-
Cabby was like,
My heart literally dropped.
You did something wrong. Do it again.
I think I did it wrong because I put 98 over there. I didn't put 0.
All right, and now we're ready then to take the negative log of this number, which is going to give me pOH. All right, so I'm going to go negative log of 0.0305, and I'm going to get 1.516.
And then you took 14.
1.516 is pOH. And then, so subtract from 14 and you get your answer of 12.484.
5.5.
Did you know?
Did you?
Is this
Yo, this is the math I've ever done.
Just run it again. These numbers are good. Run it again.
No, I know.
Wait, how do we know that it's over?
5.15,
So you mean something
I
like
think, because there's a 4 after it. It's not.
I have a 7 after mine. Did I type it in wrong?
7.
What the crap?
What do you think?
I'm feeling it. I like it. Like I'm feeling it.
Feel it like physically.
I feel confident.
Yeah, I got 2.5.
Why'd I do what? This right here? Well, 'cause I took the negative log of that number to get that number. This gave me the OH concentration. To find a pOH, you take the negative log of a concentration to find pOH. All right, we want to refocus, and again, I'm not going to finish the next problem. You're going to have to watch the video or hang out with me. But let's take a look at a strong week.
Oh, you got a fancy hat.
Can I erase?
I like how the numbers are 1, 2, 4, 5, 7, 10.
Yeah, no duh.
That's the way the numbers appear.
All right, guys, again, when the bell rings, I ask that you leave very quietly so that I can get through this as quickly as I can.
Yes, let's try to do this.
All right. We have a new titration. We're going to be adding sodium hydroxide to HOCl. All right. So right away, I can label that as a weak acid because the H to O ratio is 1:1, which makes it a weak. So this is a strong, weak problem, which is going to make some stuff look different.
How do we define the pH?
So step 1 says calculate the pH before you add anything. We did that last time, right? It wants to know the pH before the intruder. In order to do that, it's a weak acid. Does anybody remember, how do you find the pH of a weak acid?
Hydrolysis.
Add it to water.
Yes.
All right. And what I know is that my HOCl is gonna donate, while the water will accept. All right. And remember, we of course do our rice table. All right.
I'm
So my HOCl, look, had a initial concentration of 0.35. All right, and of course, it's not already a buffered system, so we don't start with any of that product. All right, we can show our shift. Now, I'm going to stop right here. Look here. Just because for the sake of time and you being in the room for some of this, this is going to be quadratic. Do you see the K value they give you? Do you see the K value they give you?
Yeah.
You're going to do that value equals x squared over this minus x. We've done a million of these together. If you want to go check your work or whatever, you're going to get a pH of 3.96.
What did we say we were going to do?
And that would be our X value.
All right, no.
No?
This your x value would be a concentration. Negative log of that would give you that. All right. So that's just a rice table. I don't mean to sell you loose on the lesson, but I've just taught this a lot. Yeah. The 3 point. I mean, just raise that to the go 10 to the negative that.
I don't understand what we're doing with the like eggs. That's what I'm doing.
It's a normal rice table. I've already tested you on this skill. That's the only reason I'm skipping it.
Is x the 10 to the negative?
Oh, yeah, that's actually right. Okay.
10 to the negative 3.96 would be it.
I don't know how to do this.
All right, so 3.96 would have been the pH for the first problem, but we don't need that value for anything else. It'll just always ask you to do that. So let's go to bullet 2, where the titration starts. All right, so my invader is a strong base, so I'm just going to write it as OH minus. The thing being attacked in the beaker is weak, so I have to put the entire thing. All right, the entire thing will be there. Normal arrow for an intrusion. Invader. I feel like I say both interchangeably. Now, this will go Bronsted-Lowry, so we know that my acid here is going to donate, and we know that the base is going to accept. All right, so here's where we can get to the point. It's a titration, right? So there's some constant stuff. All right, I know that, for example, that the water's inconsequential again, but there is something else formed when there's a weak that should start to remind you of a certain type of problem. Now, remember, my mole count of the starting guy will never change. We only got to find him one time. So let's find him. Molarity times volume. The molarity of the weak acid was 0.35. So I'm going to go 0.35 times the liters that are starting in our beaker that we're going to add stuff to is 24 mils. So times 0.024. And it looks like the mole count for the weak acid for the entire titration is going to be 0.0084. That number will never change.
And that's the mole.
That's the mole count of our starting acid. So now we want to look at the actual what's being added for the invasion. So let's take a look. It says, what's the pH? After adding 5 mils of the base. All right? Now, my base has a strength of 0.2. Do you see that? So we've got 0.2 molar in the burette that's being added to the sample. So this is another thing that won't change. This is the strength of the invader. But what will change is the amount of him that we add. On this first step, we're adding just 5 mils. All right, so let's add 0.005. And we'll get our mole count. I have somebody's graphing calculator, by the way. That reminded me. I have one in my desk. If it's got a big sticker of something on it. Anyway, if I multiply those together, I get 0.001 as my mole count for the OH. We subtract this times this is this.
So how'd you get the red amount?
The what?
The red.
The red amount was, I already erased that. It was the molarity of the acid times the volume. It was the same calculation, but with the acid numbers. There's two sets of numbers up there. This is the base numbers. These are the acid numbers doing this exact process. I subtract the smaller number because that's what we always do. But do you see something different here? We have a product that we care about.
Add.
Exactly. All right, so over here, we're going to have 0.0074. And over here, we're going to have 0.0010. There was nothing initially in there because it wasn't a buffered system. But now, it is a buffered system. Do you see the buffer?
Buffer the OCL.
We've got a weak acid with its conjugate base.
Oh.
Therefore, we've created a buffer.
We can use Henderson House.
Now, here's some good news. These are mole counts, right? We want to know pH, and we know that Henderson-Hasselbalch will give us pH very easily, but the equation says it needs molarity. It turns out that the Henderson-Hasselbalch will let you put moles into that same spot. The reason moles is okay there is because if you could go and find the liters and divide. Right now, our liters are 5 plus 24 is 29 milliliters. So we could divide both of them by that. But it turns out if you take that molarity and put it into the HH equation, you get the exact same answer as if you just take the moles and put it in there. Now, if that makes you uncomfortable, then just always convert to molarity because that's what the equation says it wants. But letting you know that if you go strong-weak in a titration, you can absolutely use the mole counts in the equation. Therefore, we can go pH equals negative log of, there's my constant, 3.5 e negative 8.
Does it matter which one is the stronger weak?
Nope. I mean, it's going to, no, it doesn't. All right. Plus the log. All right. And here's where you got to be careful. What over what?
0.0384 over.
Yeah, the ion, the one with the charge goes on top
Oh.
over 0.0074.
Oh, yes.
And that will give you the pH. I get 6.59.
I really need to study that.
When can we not use moles? So, because in the last video it said
No, because in the last one we had to have a concentration in the last one to find pH because we were using negative log, which demands molarity.
no, sorry, in the last season, intruders, we had to use molarity.
You remember you put not moles on the notes.
Intruders.
The intruders, you put not.
I can't. You'll have to show me the exact problem you're talking about. I don't have my bearings now. Watch. Hey, watch my erasing this time. I'm gonna leave that there because I know it's gonna ask for pH again, and I'm gonna leave Henderson-Hasselbalch up here also because the only thing that's gonna change as the titration continues is those numbers. That's all gonna stay the exact same, right? I'm also gonna leave the 0.0084 up there, all right, because we know that we're not altering our starting amount of weak acid. And now I can just keep altering this information for the continued invasion. So let's go again. My next invasion is 15 mils of the base. All right. As we said, the base is going to be 0.2. All right. So my base is sitting there at 0.2. But this time, it's 15 mils being added. All right, so there's my 15 mils that we add to get me a new mole count. That was my initial mole count when I did 0.350 times 20.024. No, but it doesn't change. That's what it became after you added that first amount. But we're not then adding that amount again anymore. We're adding to that amount. We added 20, which got me down to that level, and then 20 more. So just my value here is going to be 0.003. All right, I'm going to subtract the smaller number.
It's 0.0054.
And now I've got mole counts for both parts of my buffer. I already have Henderson all set up and ready to go, so I'm going to put my ion up here. I'm going to put my weak species down here. And it's going to spit out a pH this time of 7.20.
Ready? Got it?
For that's the pH for that step. Now, it has us do 2 more titrations. I'm just going to do one of them for the sake of time because it's just repetitive. So I'm going to skip the 25 mil and just go to the 35 mil because why not? So again, I'll selectively erase my
Wait, pH.
7.20.
I rewrite them because you have a board.
Yeah, I know. I definitely have an advantage over you. All right, so let's do another one. This time it's 35 mils of base. So I need a new mole count.
There's only really one like this on the test.
There's
one.
one, but it looks exactly like this.
Okay, that's what I'm saying, but like only one because my hand hurts.
All right, so my starting molarity was 0.2 of the intruder. This time we're adding 35 mils. That's 0.035 mils, all right? To get a new mole count of hydroxide. This time I'm gonna get a mole count of 0.007.
What numbers do you multiply?
I'm sorry?
What numbers do you multiply to get that mole count? You use
To get the mole count, it was 0.2 because that's the continued molarity times 0.035 because that's the amount that's been added. All right, we're going to subtract this guy, it looks like. .0014. So we've got our new mole counts. Henderson Hasselbalch will allow moles. So let's go ahead and put the ion over the weak species.
I got 8.15.
And I get 8.15.
Okay. Seems simple.
All right, and now we've got these other types of questions at the bottom about equivalence point and stuff. So let's take a look at that.
I mean, we have to equal it to each other.
I'm sorry?
Equal the point of
Right. So I will start to erase. Now there's some
Are we on a 6 point?
we've got some unfortunate truths that are going to haunt us right here, though.
Wait, what point are we on?
I'm on point 10.
Wait, what did we just do?
Wait, hold up.
Well, X, the one that says X.
Which one did we just do?
We just did the 35 mils. Now we're on the calculate the base needed to reach the equivalence point, the volume of. So let's just take a look at what that looks like. We need our moles to be the same, so 0.0084. All right, they're the same number, so that's an equivalence point, right? So of course, what will happen? Well, this will happen. Now, we didn't really have to do all that to figure out the answer to this question, but it will be important in a moment. What this wants to know is how much volume do you have to add to get to that number? All right, well, our equation that involves molarity is this, and I've got two of the variables. I know that the molarity of my hydroxide, my strong base here, has been 0.2. I know that the mole count for the equivalence point is 0.0084. What I don't know is how much volume needs to be added in order to get there. But what you will calculate is that the equivalence point volume is 0.042. liters, which is going to be 42 mils. The answer to that bullet.
Oh, no.
There's 2 bullets still.
I can't see the thing.
I'm just going to take a picture of it.
Well, it's on your slides though.
What?
Oh, you're taking a picture of what I write?
Yes.
Well, that's why the video will be nice. You can pause. Okay. So continuing on. Now, last time when it was strong, and I asked what the pH was, the answer was 7, right? Because all that was left was water. Do you see why we have a problem?
Because there isn't just water.
I mean, it's going to be basic, right?
What we have sitting here now is the kiddo of a salt. If we want to find the pH based off of something connected to salt, what's required? That's right.
Parent.
Hydrolysis.
That's all. I was like the parent, the hydrolysis. Dang man.
The only way to find pH is to do a hydrolysis rice table. So, we can do that. Let's go OCl minus, add it to water. All right, it's going to end up producing HOCl and hydroxide. Oh, dang it, I erased that number. I needed that number.
Isn't it the same?
0.042?
No, because we got rid of this. Like this right here doesn't exist. It's the OCl concentration that was added. Oh no, it was that number, 0.0084, right?
Yeah.
Oh, I see what the problem is. Okay, so
Wait, so
we're building a rice table here, right? Well, if we're doing hydrolysis, we are. All right. What kind of value has to go into the I column?
the initial concentration.
The initial what? Concentration. Therefore, I can't put those moles in there. So while the OCl minus was sitting there at 0.0084, 0.0084 moles, to get concentration, I need to divide that by liters. And here's where we need to figure out how much stuff we've added. Hey, look.
Did you just turn them around? Did you switch it? You put OCl plus H2O first, and you put the product.
Yeah, but this is hydrolysis of. Oh, yeah, this is, yeah. But no, look, this is different.
No.
Quit looking at that.
Oh.
This is the hydrolysis of the ion.
For it to produce the OH and
I added him to water, and that's what happens.
Yeah.
All right? The 42 mils were the equivalence point, right? Was the 42 mils? But that was added on top of the initial 24 mils that was in the beaker. So what is the actual liters that's in the beaker right now? All right, it's sitting there at 66 mils. Again, that 66 mils right there is the equivalence point, the 42 mils, all right, which got us to this part of the problem, plus the 24 mils that were in the beaker when the problem started. 66 mils, all right? Therefore, when you divide those two values, you're going to get 0.127. Or really 0.13 with sig figs as your molarity there. All right, so we can show our shift. All right, so we're trying to find pH. Our X down there is connected to hydroxide, I can see. Now, what do we know is always true in hydrolysis? It's going to give us an unusable value. So we've got Ka. It gives me a Ka in the problem of 3.5 E negative 8. Yeah, but we need Kb. So what we can do then is use our Kw. So we'll go 1 E negative 14 divided by 3.5 E negative 8 is going to give me a Kb.
2.86.
What did you get?
2.8 and 2.9 E negative
2.9 E negative 7. Did you get that, Diego? I don't have that written in my notes for some reason. Yes. All right, there's my Kb. And now we can set that equal to all of our good stuff here, which will be x squared over 0.13 minus x.
It equals 3.77.
All right, so we'll end up with a 0 equals equation of x squared
Plus 2.
plus 2.9 e, it's negative 7, right?
Yes.
Yes.
E negative 7x minus, what do you have a value right there, Annalise?
Yes, 3.8 E negative 8.
All right. You'll type that into solver.
I got 1.9. Whoa.
1.9 e negative 3. Scroll over.
I got 1.95 E negative 4.
1.95
E negative 4.
e negative 4 molar.
Yeah.
So keep in mind what you found there. X is the concentration of the hydroxide. All right? So if we go negative log of that number, it'll give you POH. So I'm going to go negative log 1.95 E negative 4.
3.7.
Yeah, I get 3.71. 3.71 is POH. Of course, the problem wants pH, which will come out to 10.29. So we have a final pH answer then by subtracting from 14. No, there would only be one more, but I'm gonna go eat, and then I'll post
How
the
do you
answer.
get the,
Bye, everybody. I love you.